So far we've been using the iterated or double integral to look at either area of a plane region or volume of a solid that sits above a plane region and below a surface. Before we get into another application that's very commonly used with multiple integrals, I have to kind of go back to a very rudimentary physical science topic before we move forward. So we're looking at trying to find the center of mass of a two-dimensional region. Where would its balance point be? So a piece of paper may have a center of mass that's literally right in the middle. There's no other marks in the paper. If the density is constant throughout everywhere, you just measure the middle, that's the center of mass. But if there's ink on one portion or holes cut out or something else that changes the density, the center of mass may be somewhere else. So before we get into variables, let's just look at some very basic skills. So consider a number line, the x-axis, and there's the origin. And we're going to look at a point that is 4 units to the left with a mass of 6 units. So mass could be measured in grams or kilograms. Remember, pounds are a unit of force, not a unit of mass. So we're looking at mass here. And we would say that this point, with this mass focused on this point, relative to the origin, has a moment that is its location multiplied by its mass, or negative 24. The negative actually gives an indication of location to the left. A positive would indicate to the right. So plus and minus have a definite meaning here. So I can't call it distance, I have to call it location. So there's several things you can do with this, and we'll call it at the physical science level. Let's suppose I had another point over on this side that was located at x is 3. So one of the questions we could ask is, what should its mass be? What would that mass be in order for the balance point to still be at the origin? So simply put, not necessarily accurate in a physics sense, but just simply put, if this has the same moment, but on the positive side, then these two points would balance out over the x equals 0, or the origin. The concept of a moment is for forcing some sort of a tendency to rotate around this point, so like the scale tipping one side or the other. So in order for this to have the same moment, we would want the x value times its mass to be equal to a positive 24. So we have x is 3, and we have an unknown mass is 24. We would want that mass to be 8. If this mass was 8, then you would say that these 2 points would balance at the origin. Now, a little bit further with this concept. If there were more points than just these 2, we would say the moment about the origin and I'll use simplified or pseudocode notation here, you would find the sum of all of these various x values and their mass values. So if there were a dozen points in various locations with varying masses, you would add them all up. If we had a positive value, then that means the center of mass would be somewhere to the right side. And if we had a negative value, then that means this thing would balance out somewhere to the left side. And if we get 0, then that means the origin is truly the center of mass. So, this is our basic concept or basic formula. Now, the mass itself of this system is nothing more than the sum of all of the separate masses. Nothing more than the sum of all the separate masses. So let me scroll back up to my example here, and let's change this problem a little bit. All right, so this is what the case would be if the center of mass is at x is 0. But let's suppose this had a mass of only 5. Let's suppose this have a mass of only 5. So our moment in our particular case would be -4 times 6. Of course, that represents the first point we looked at, plus location 3 with mass 5, -24 plus 15 is -9. Negative would indicate the center of mass is somewhere to the left. Well, the total mass of this system is nothing more than 6 was the first one and 5 the second one is 11. So the calculation for the center of mass is found by taking, first of all, notation, x with a bar over it. I'm going to just call it x bar. By taking the moment we calculated divided by the mass we calculated. And for this problem, that is -9 over 11. That would be the location where this system would balance out. It's about here, left and right. The moment to the right of that point would be the same as the moment to the left of that point. One little thing before I end this section. Notice this notation is the same notation as for average or the arithmetic mean. And we find the mean by adding up the list of quantities and dividing by a total. Well, these were the sum of all the moments divided by the total mass. The notation from statistics and probability seems to fit well here. The next section we're going to look at will be to do this in 2 dimensions, so stay tuned.